So I would like to welcome all of you to hypothesis testing and inferences, the evidence of knowledge is result. What we are going to do is this. By the end of this lecture, you should be able to develop a null and alternative hypothesis. You should be able to formulate a decision rule, know how to use the test statistics, how to calculate the critical value and the p-value. Know what type 1 and type 2 errors are. Compute the probability of a type 1 error. Understand inferences about difference between two means, not just one mean, but two means. And then you will know the equivalents. And these equivalents we will not do them this semester, we'll do them next semester. So let's get rocking, let's get to running. Let's look at a certain real life situation. Is the new manufacturing process better or more reliable than the old one? You want to know. This is a question that requires hypothesis analysis and inferences to be made. Another one. What is the likelihood that temperatures will be more than 20 degrees Celsius on a specific day? This is a question on hypothesis. Does the training workforce improve sales or it does not? What is the likelihood that the website conversion rate will be above a certain percentage next month? Especially when you want to drive traffic to your website. Oh, Esther, I was saying that you should post it in the WhatsApp group page. A bulb manufacturing company is interested in knowing whether the new manufacturing process improves reliability of bulbs. This is a hypothesis question. So, ladies and gentlemen, we want to look at some of these real life scenarios, but let me pick you from a real life situation. Suppose you went to a supermarket, let's say Accra Mall, to buy a packet of juice, and the juice is 500 milliliters. Now, after reaching home, you realize that the weight in the juice seems to be lesser than you thought. So what you did was to measure the volume, and then you found out that the juice was not 500 as stipulated, but it was 478 milliliters or milliliters. Then you search on the internet and found out that the company claims to have 490 milliliter juice in the box with a 10% ml of standard deviation. That was their claim. But in your packet you had, the juice quantity was quite less than what they have purported. Question is, you want to know if this just happened by chance or the company's claim is wrong. This is a question on hypothesis testing. So hypothesis testing is actually for your personal use. But it's more than that. It's for company use, it's for government use. If you understand it, you can be a good consultant with it. I've been using it in a number of my consultants. Let's look at another real life situation. If you want to test a research hypothesis, most of you will be writing theses or dissertations or project work or long essays. You want to check whether a new car, the system increases the mean miles per gallon performance. You want to test the validity of a claim. For example, a manufacturer claims that 1 liter soft drink bottles are filled with an average of at least 0.99 liters. You want to test a decision from a business. For example, a new online advertisement has led to higher online conversion rate for an e-commerce website. That's what they claim. And you tend to see some of these things in a lot of adverts. Ours is the best, mine is the best. Ours is, you want to test. You want to test. Why do we need to understand hypothesis? Well, first of all, a hypothesis is a statement or a guess about a population parameter. So for it to be a population parameter, it means that it's existing and you want to know about it. And the thing is that you don't have prior knowledge about the population parameter. Actually, the population parameter is normally unknown. A random sample is usually supposed to be taken, mimic what the real world looks like. It's called bootstrapping. And then a sample statistic is computed, and then you select an appropriate point and an interval. And then you check that against the population one. And then you come out with it. So why hypothesis? Because we have no knowledge of the population parameter. The goal of a hypothesis, therefore, is to set a value for the parameter and perform an analysis to check whether that parameter you've set is tenable in the light of the evidence gathered from the sample. Guys, let me ask you, will the NDC win the next election? I need an answer. Will the NDC win the next election? What do you say? Will the MPP lose the next election? Whatever answer you have, tell me. Will the NDC win? Whatever answer you said is a conjecture. It's a guess. You have to prove it. People always say things without giving proof of it. And whatever they say is accepted. A lot of people thought that Donald Trump will not win, and yet they have failed. You have to have facts before you make a claim. That's why we need to have hypothesis analysis. So what are the steps in hypothesis testing? Well, the first thing is to know the population parameter. If you don't know, you got to know it. There must be something existing already before you came. Then you formulate the null and the alternative hypothesis. You will learn how to do that. Then you find a decision rule in your head already before you start. Then you calculate the test statistic and then compare that test statistic with a critical value. You calculate the p-value and compare the p-value with the alpha. And then you decide and conclude. Guys, let me pick a few things before we move on. My major thing that I want to pick here before we move on is the p-value and the alpha. Anytime you are doing a hypothesis, the alpha, which is also called the level of significance, the risk of drawing an incorrect conclusion, that alpha is like the error you are expected to make in your analysis. Write it down, you forget. Because what I'm saying is practical to me. So when you're undertaking an analysis, you are expected to make some errors. The error you are expected to make is the alpha. If the alpha is the error you are expected to make, then the p-value is the error you actually make. So the alpha is expected error. The p-value is the actual error. Question to you. Which one do you wish is smaller? The p-value or the alpha? Which one do you wish is smaller? Is it the p-value that you wish is smaller, or is it alpha that you wish is smaller? The p-value. Good. Now, we're going to see. So each time you're expecting the p-value to be smaller, it means that you made a little mistake, and so you have enough gravitas to reject the null hypothesis. After that, you decide and conclude. These are the steps. Let's start with the null hypothesis. What is that? It's an authoritative statement about a population parameter. It is assumed to be true all the time. It is a status quo. It's always assumed to be right. It is said that until proven guilty, this man is not guilty. That's what it is. Until the judge will hit the thing, bam, bam, bam. You cannot say that a man is a criminal. That is a null hypothesis. The null hypothesis always carries some level of equality. Take note, write it down, you forget. The most dangerous thing in lecture is when you're just watching and not writing. The null hypothesis always has some level of equality in it. So whether it's less than or equal to, or greater than or equal to, it is the null. That is what carries the null. You can reject it or you cannot reject it. Let's go back to the company's assumption. The company claims to have 490 ml juice in the box. That is a null hypothesis. Now, looking at the statement, which of these some level of equality will it carry? Is it going to be equal to, less than or equal to, or greater than? Which one? Which one of these would have been the symbol to use? Samuel says equal to. Tracy says equal to. Which kind of symbol would this be? Eves says equal to. Frederick says greater than or equal to. Esther says equal to. What do you say? Samuel says equal to. Efua says equal to. So that's it. It is equal to because that statement has equalities mind. The company claims that or claims to have equal to 490 ml. That's it. Now let's look at the alternative. The alternative is a mirror image of the null hypothesis. It questions the status quo. Okay. I think I made a typo. It contains not equal to. It shouldn't be equal to. It contains not equal to or greater than or less than symbol. That is what it contains. And it may or may not be rejected. Is a hypothesis believed by the researcher. That's what a researcher is going for. That's why he's doing his work. So the juice quantity is not 490 ml. What symbol is that? It's not 490 ml. What symbol is that? What symbol? Less than is not correct. Not equal to is the right one. Very good. So take note on how to write the null and alternative. The next thing about hypothesis testing is to know the tail of the test. There are only two tails and one tail. Two tail, and they always come from the alternative side. So that whenever you have greater than symbol, you know, or less than symbol, you know it is the one tail. And these are the alternatives to the usual null hypothesis. These are the alternative hypothesis to the null. Whenever you have not equal to, which is an alternative of equal to, that is said to be a two-tail. A one-tail has got one side shaded, as you can see here. A two-tail has got both sides shaded. Remember, the normal distribution or the T distribution is a mirror image. It's a mirror image. Let's take a particular real-life situation on how hypothesis works. The manager of Peduase Lodge stated that the mean guest bill for a weekend is at most 1,200. A member of the hotel's accounting staff noticed that the total charges for guest bills have been increasing in recent months. The accountant is considering using samples of future weekend guest bills to test the manager's claim. Formulate a null and alternative hypothesis. Do a complete analysis. Use both the critical value and the p-value approaches for that. So first of all, what I want to ask you is this. What will be the null and what will be the alternative hypothesis? Well, the first thing is to look for the symbol that is at hand. That symbol comes from which word? Which word here is a symbolic word? Who can tell us? Looking at the first one, the first bullet, which word here is a symbolic word? The word. That word is at most. That is a symbolic word. Now you ask yourself, what symbol is at most? What symbol is at most? What symbol is that? At most? What symbol is at most? At most, somebody is writing alpha, really. Someone is saying greater or equal, someone is saying less or equal to, someone is, okay, wow. At this level, guys, you got to sit up, honestly. Honestly. So at most, it's less than or equal to. So that's what you write first, less than or equal to. At least is greater or equal to. Once you have written the symbol, put mu, because that's always representative of the population, in front. And put the number in question to the right. And the number in question is 1,002. Then you do the same thing with the one below. But before, leave a gap for how you will write the alternative. What is the opposite of less than or equal to? That's what you ask yourself. Because less than or equal to is the thing, but what is the opposite? That should be below. The opposite of less than or equal to is what? Samuel, Mariam, Mary. Okay. All of them said greater than. So you write it down. Then you bring a colon in front of each one of them. And then step back. Ask yourself, which of these two information carries some level of equality? Is it a top one or the down one? Which of them two carries some modicum of equality? Therefore, which one is a null hypothesis? Which one is a, when you're sitting down and others are typing, but you're not typing some, it doesn't make you get engaged. Your brain will go dead. But the more you type some, the more you type some, the more you type some, I tell you, you are energized. Okay. So the first one is going to be the null hypothesis, and the alternative will be the down one. The next question. Nescafe claims that since the population mean filling weight is at least £3 per can, consumers' rights are protected. How will you formulate the null and alternative hypothesis? Well, look for the keyword. The keyword is at least. What symbol is at least? Greater or equal to. What is the opposite of that symbol? Less or equal to. Bring your mean in front of each one of them and write the number in question, in this case, £3 per can. You ask yourself, which one has some level of equality? Is a top one. Therefore, the top one is a null hypothesis, and the down one is the alternative hypothesis. Remember, this carries 5 marks all the time, 5 marks. So master how to write a null and how to write the alternative. Next question. You see, remember, this is just the first step in hypothesis test. You also have to understand the errors that can be made when you are doing hypothesis test. If the null hypothesis is true and you go ahead and still reject it, you have committed a type 1 error. If the null hypothesis is false and you go ahead and you don't reject it, you have committed a type 2 error. If the null hypothesis is true and you go ahead and reject it, even though it's true, you've committed a type 2 error. Actually, it's not you've committed a type 2 error, you've just committed an error. And then if the null hypothesis is false and you still reject it, because you've just rejected a false one, which is good, okay? You've not committed any error. So take note of this error. I mean, 2 of them are the main ones, okay, not the other ones. Okay. What is the probability of committing a type 1 error? It is the alpha, the level of significance. Alpha is the actual mistake. And the lower the alpha, the higher the confidence. Because the 2 of them will give you 100%. So if alpha is 2%, then it means that the confidence level is 95% and 98%. If alpha is 5%, the confidence interval is 95%. So just know that the relationship between the alpha and the confidence level. The probability of committing a type 2 error is beta. Now, type 1 error, which is alpha, watch this. Alpha, you can specify alpha ahead of time. There are 3 main alphas in the world. 1%, 5%, 10%. You can specify it ahead of time before you even do the analysis, but you can't do that with the beta. Because the beta depends on some unknown parameter in the population. First of all, the population itself is not known. But there is a way you can sense beta, even though you don't know it. Because anytime alpha is falling, beta is rising. Anytime alpha is rising, beta is falling. In fact, when you look at the first 2 bullets here, it will make sense that. So just remember these errors because they are necessary when you are doing hypothesis tests. The next thing to know is the result, outcomes, the possibilities, and the state of nature. A table will give you everything we are talking about so far, about errors. So let's say that you are doing a hypothesis. You have the level of significance, which is the alpha. The null hypothesis is true. You still go ahead and reject it, even though it's true. You've committed a type 1 error, and that is the alpha. The null hypothesis is false, and you're supposed to reject it, and you still fail to reject it. You've committed a type 2 error. Anything outside this is a correct decision. And the power of the test is based on when you make a correct decision. The power of the test is when you make a correct decision. Let's find out about the type 1 and type 2 errors. I'm giving you a statement. Let's say that you have a null hypothesis here that says the patient doesn't have cancer. That's it. What do you think the alternative hypothesis would be? If the null says the patient doesn't have cancer, what do you think the alternative hypothesis for this statement will look like? You can talk anytime. The patient has cancer. The patient has cancer. Very good. You all said the right thing. So, look at the statement. The patient has cancer. What would be the type 1 error? Remember what a type 1 error is. The null hypothesis is true. You go ahead and you reject it. Sorry, the type 1 error. Yeah, the null hypothesis is true. You go ahead and you reject it. How will that statement look like here? I'm seeing some interesting answers. Type 1 error saying, you can just say T1, saying the patient has cancer. The patient doesn't have cancer, but is diagnosed of cancer. Rejecting the statement. No, don't use it. Make it practical. Make it practical. Okay. I've got my answer here, which is a really, really smart one. This answer is called false positive. False positive. The patient doesn't have cancer, but the doctors are saying that he has a cancer. That is a type 1 error. Why? Because the null hypothesis is that the patient doesn't have cancer. So if the null hypothesis is true, then it means the patient doesn't have cancer. But you are rejecting that statement. You are committing a type 1 error means that even though the doctors are saying that true, the patient does, the patient doesn't have cancer, the doctors go ahead and still say that the patient has cancer. And that is committing a type 1 error. It's a false positive. The other one, of course, will be a negative. What do you think type 2 error will be here? Type 2 error. That is if you are not copying from anywhere. What do you think type 2 error will be? Remember, type 2 error is when, let me see. Someone said the patient has cancer. Sir, please come again. Tracy, which come again are you talking about? There are so many things I've said.
Yeah. Sir, please, you spoke about the type 1 error. I didn't get that part. Can you come again? Can you explain it again?
Type 1 error, and as you can see here, says that the null hypothesis is true, but then you rejected it. So it says that the null hypothesis is true, but you still go ahead and reject it. And what is true is this. The true is that this statement, the patient doesn't have cancer, is true. The patient doesn't have cancer is true. And you are telling me that that is not true. So the patient doesn't have cancer, but someone or the doctors say that the patient still has cancer. They are committing a type 1 error. Does it make sense? They are committing a type 1 error. Because if the patient doesn't have cancer, and that is the truth, if you tell me anything otherwise, you committed an error. Now, type 2. Okay. Type 2 error. Okay, let me see what others are writing. You know what type 2 error is? Type 2 error is when the patient, okay, so watch it here. It's when the null hypothesis is false, but you still say it's true. Let me see what some are saying. You don't write some. Your colleagues are writing. You don't write some. The patient doesn't have cancer, but is reported to not have cancer. Doesn't make sense. He or she has cancer, but has been diagnosed he doesn't have cancer. Okay, the patient has cancer, but doctor says patient doesn't have cancer. Okay, the patient has cancer, but is reported otherwise. The patient has cancer, that's from Esther, but was diagnosed the patient. I think you're all cracking this one. You are all cracking that. So that is type 2. The patient doesn't have, but the report says the patient does have it, but the report says she doesn't have. It could be slightly confusing sometimes when you don't take care of it, but just understand. In a multiple choice, there are so many mistakes people make between type 1 and type 2 errors. So how do you improve the power of your test? Because you could make an error or simple. In a practical situation, you want the power of the test to be high so that you can conclude validly. Because the power of the test is very sensitive to the size of the sample. If you go and collect a small sample size, you're in trouble. It will lead to a very low value of the alpha. So you need the sample size to be big. Why? Because when there's some errors are taken from the bigger one, you still have some left. Because you'll be able to tell small differences between the sample statistics and that of the population. Remember, you don't know the population, so you collect a sample to be closer, so that whatever you say will be closer to the population. If you go and collect a small sample, it is as though you don't have a population. You don't even have anything that will be closer to the population at all. But the level of significance, which is the alpha, you have to choose. That one we said you have to choose. If you choose a smaller one, always compensate that with a larger sample. So suppose you choose the level of significance to be 0.1%. Wow. So you are saying that I'm going to make 0.1% error, which means that I am expected to A. Then it means that your sample size must be big. Okay. The sample size must be so big so that what you have chosen will be good. Because if you go and choose a small sample, they will punish you. They will punish you. And that is what you have to understand when it comes to the power of the test. It is connected to the sample size. The next thing now is after you've decided, you have to select a test statistic. Before you calculate the test, there are several test statistics. The decision to reject or not reject the null is based on calculating the test. And the type of test is important. Why? Because some of the tests, you can't use them for some of the things. For example, in a one sample test, the standard deviation is known in a one sample test. Okay. In one of the one sample tests, the standard deviation is known. But in another one, the standard deviation is not known. Now, if the standard deviation is known, then you will use this Z formula. But if the standard deviation is not known and the sample is large or small, then you have to use T. So if the standard deviation is known, then it means like you have everything, you have the population. So you don't even talk about sample again. But if not, then you have to talk about the sample now. In that case, T is always used. Don't worry, there's a connection between the T and the Z, so you can use the same table for both. Now, how large is large? Large is large when the sample size approaches or is more than 30. So when the sample size is more than 30, that is when you know that it's large. If it is less than 30, it's not large. So take note of that. The next thing now, after you've now decided on the test, is to now calculate the test. And then after calculating the test statistic is compared to the critical value. You compare the two, and it's just like comparing the confidence interval with the actual mean, comparing that. And then based on that, check whether it's a one-tail or a two-tail. You create your normal distribution curve. The extreme ends are always rejection region. The middle, big space, is always the acceptance region. Now, if the tail is 1, then you only focus on one side of the region and ignore the other side. Then come out with your conclusion based on where the value falls. Let's take an example. Follow me here. In a study, the study was entitled, How Undergraduate Students Use Credit Cards. It was reported that they have a mean credit card limit, watch the word, limit of $31.73. Assume that a current study is being conducted to determine if it can be concluded that a mean credit balance, which is the same as the limit, but undergraduate student has continued to increase compared to the original report. Based on previous studies, used a population standard deviation of 1,000. Given a sample of 180 undergraduate students with a sample mean credit balance of 33.25. State the null and alternative hypothesis. Use both the critical value and the p-value approaches. Use 95% confidence interval. And before you even formulate the null and the alternative hypothesis, you must always identify the 5 elements of the question. The first one is to identify which is the population mean and which is the sample mean. Now, how do you know which is the population mean and how do you know which is the sample mean? Oh, by the way, who can tell me what a population mean is here without copying from anywhere? What is a population mean? Yeah, what is the value of the population mean? That's my question. You see, I have 2 different answers. That should tell you there is no joke. I'm getting 2 different answers. Type some more. I want to know which one you think is a population mean. Okay, who can tell me? So the population mean is 31, 37, 73. Question is, what makes you think that this is the population mean? Why? Because it could be a guess you are just doing there. Marion, Samuel, Eve, Tracy, and Rita, as Ajua, all of you are guessing. Prove to me you were not guessing. Who's bold? Who's bold? Marion has made a very good answer. The sample mean always has the standard deviation following it. It comes along with the standard deviation. So the sample mean comes along with the standard deviation. The population mean does not come along with the standard deviation. So where is the standard deviation? It was spoken of here. And based on this standard deviation, you were told that the sample was that. And based on that, you were told that with a sample mean, it was even mentioned. But even if you have not used the word sample mean, you would have known that that is a sample mean. Therefore, the population mean is a 3173. So the population mean is a 3173. Write it down. The sample mean is 3325. What is the sample size? Sample size is 180. And the standard deviation, that is 1,000. So this information should be written first. What is the value of alpha here? What is the value of alpha? Exactly. Marion and Della cracked that. 0.05. So that is the value of alpha. With all of this information ready, you are now ready to formulate the null hypothesis. Of course, we are going to use the population mean to formulate the null and not a sample mean. So we are going to use 3173 to do the formulation. What symbol is at play here? What symbol are we going to use to document this whole population? What symbol? What symbol will be used to make statement clearer? It comes from the storyline. There is a word. Okay, what word? What word? Let's get a word first. I see most of you are writing equal to, equal to, equal to, equal to, equal to. A baby Joe. Okay. What word? I see equal to. The word is limit. And so if the word is limit, what does that tell you? If I say that the limit is this, what does that tell you? No. No, less than is not the limit. It is less or equal to. If I say that, if I tell you that the limit, oops, let me just clear this. If I tell you that the limit of something is 3173, that is, the limit here means how far you can go up. How do we know it was up? Look at it. It says that the current, assume the current study is being conducted to determine if it can be concluded that the mean credit balance has continued to increase. So you even have a clue. Okay. You have a continue to increase. Now, if increase is greater than, which you all know, then the limit is less than or equal to. That's a clue. So the word limit, even if you don't understand what the limit is, okay, the increase here should give you the clue that is the opposite of the one that was mentioned. So knowing very well that that is the case, the null hypothesis is going to be which one? Okay, so now first thing you got to do is to formulate your hypothesis. And how do you formulate the hypothesis? The hypothesis must be having your greater than, because that's what you got. But the word limit, if you understand it, that's the one that will come. Okay? So limit is that, and then increase is that. So you have the mu, and then you have the mu, and then on the right-hand side, you have 3173, and another 3173. Which one is the null? The top or the down? I think by now you all know. Okay, so the null is going to be the top one because it has some level of equality. The alternative is going to be the down one. That is how you do it. Now let's go and look at how we did it, because it's not just writing. No. No. I'd actually wanted you guys to think small. Apparently, it looks like I didn't put this information there. So let's do it. Let's do it together. Let me go here. Okay, and let's do it. So the null hypothesis is going to be mu less than or equal to 3173. The alternative is going to be mu greater than 3173. Now, what does that null hypothesis mean in normal, simple English? Because the way you understand it, the way you say it in English matter, there's too much for that. Okay, what that means, the first one means that the average is not over 3173. So the average bank balance is not over that. You cannot exceed. The average is not. There is a limit of 3173 bank balance for the students. So in English, you write it that the average is limited to 3173. And how will you say the second one? You will say that the average has gone past, because that's what they were saying. It's gone beyond the limit. Now, that second one is very important because that second one tells you something. Okay? In other words, there's a lot of evidence that exists to support the claim, which is really, really good. Okay? So the average has increased beyond, the average has gone beyond 3173. Now, identify whether this is a one-tail or a two-tail. What would you say? Is this a one-tail or a two-tail? One-tail or a two-tail? One-tail or two-tail? This is a one-tail. Perfect. You're all getting that correct. Why? Because anytime you have this symbol, okay, and we are talking about the symbol which is greater than or equal to, it means that we are dealing with a one-tail. Next thing, are we going to use Z or T? You always have to ask that. And you can go to the question to guide you. Yeah. Okay. Are we using Z or T? Looking at what information? Are we using Z or T? Looking at what information? Who can tell us? Z or T? Let's see some of the answers. Z, perfect, because the sample is larger than 30. So put that there. You're using Z. Now, what is the level of significance? We've already said that the level of significance is 0.05. Good. Now, what formula are you going to use to solve for the test statistic? So that's your first thing. Well, the formula for solving for the test statistic is given by Z equals to X bar minus mu over the standard error. Over the standard error. The standard error is given by the sigma, so this one was given, divided by the square root of n. Sigma divided by the square root of n. You substitute all of the values. What is X bar? X bar was given us, when you go on top, 3325. So please take your calculator and solve it. You get 3325 minus 3173 divided by 1000 divided by the square root of 18. Calculate and tell me the z-value you have. This, by the way, is known as the test statistic. The test statistic. What did you get? See, the way you punch your calculator matter. The way you punch that calculator matters a lot. It matters a lot. So when you do that calculation very well, I can see Mari has done well. I can see Delagos stuck, so he's left it for me to do it for him. You're very funny. I think I came to save you in this world. So when you do that correctly, you're going to get 2.0392. That's what you get. Okay. Your answer is going to be 2.0392. That is your z value. That is your z value. Let me rewrite it again before somebody comes to say. So your z value is going to be 2.0392. Okay, so this is a test statistic. Now we need to find the critical value. And you want to pay attention here. Ladies and gentlemen, there are basically three main critical values when you are dealing with Z. You don't need to calculate too much, but I'll show you how I got a 3. Anytime you are dealing with Z, okay, and you have Z with a subscript of 0.01, that is 1%. Okay. Anytime you have Z and then the alpha is 0.01, that's one Z you can have. Then you can also have another Z where alpha is 0.05. Then you can have a third Z where alpha is 0.1. There is a standard table that can give you the Z value for all of this automatically. And now I'm going to show you the standard table. Let me see if I can go to the PDF. And show you. Where is my PDF? Okay, just a second. So, all of a sudden, my PDF is not trying to show, so let me just open. So I'm going to show you the table that is nice to exhibit. I'm sure you could see this table here. So this is a Z analysis that you're going to use. So watch it. Okay. You're not going to use this Z1. You're going to use the student T distribution because the student T distribution also goes beyond 30. So anytime it's going beyond 30, that picks it up for the Z. Okay. So look at this table. I know it looks small, so I'm going to make it bigger. Okay, so that you can see the exact table I want to use, this one. Okay. So when you look at this table, the 0.01 for a two-tail, that is this. Okay. For a two-tail, the 0.01, this is the value, the 0.01 for two-tail. For a two-tail 0.05, this is a value. And for two-tail 0.01, a 0.1, this is a value. Now for a one-tail, okay, 0.01 is rather here. 0.05 is rather here, and 0.1 is rather there for one tail. Now, what you do is that you take the Z value by following these pointed down. Let's start with the two tail. So if you are dealing with a two tail and your alpha is 0.01, you will go down this pathway. Let me see if I can use it. I need to make this a bit smaller. We should change this, but don't worry. I need to go a bit smaller. Okay. So the only option is I come here. I just want to show you this thing well. So for 0.01, it goes down this pathway. That's 0.01. And then as it goes down that pathway, it will meet this value that you see, this value here. This value. And what value is that? Okay. Let me just undo, then you can appreciate it. So the value is 2.71, 2.576. 2.576, that's 0.01. Okay. So the 0.01 will give you this. Now, when you're looking for 0.05 for two tail, you start from here, two tail, and keep coming down until you get this one, which is 1.96. Okay. You get this 1.96. And then for 10%, 0.01 is just beside it here. You keep coming down, and that will give you the last infinity values is what you're taking, 1.645. So that's how you do your reading for the Z values. So now we are looking for 0.05. So that means that we need to take this value for two tail because we are dealing with two tail. That is 1.960. Let me be sure. Yes, 1.960. Okay. Now let me go back to the slide. So two tail is what we have been doing. And now that gives us a value. Did I take the, oh, we're dealing with one tail, right? See, you see why you people don't talk? Those who don't talk, they don't talk. And you know, I'm toggling between a lot of things. So anyway, so one tail, you have to choose this one, which is one tail, 0.05 here. And when you come down, you get 1.645. So when you zoom, you see that the value we are dealing with is rather 1.645. So our answer, our T answer is going to be 1.6. Looks like you guys were not even seeing it. 1.645. So when you read, that is what you're going to see. 1.645. So let's look at this. So we get our hypothesis, we get our calculation, and then these are the several Z values that we have here. Okay. And that gives you 1.645. This is a two tail. Two tail, but we are dealing with one tail. So one tail is here, and you can see that we need this value, which is 1.645. Once you have that value, you need to draw this curve. Okay? And then you identify here as the rejection and acceptance region point. We call it the decision to reject or not to reject. If it's a two tail, you do the same thing on the left. Then you put that 1.645 value here. I've told you the critical value is going to be one of these, just one of these, if it is a one tail. And I also give you the one for the two tail. So now you identify that junction as the value you found, 1.645. Then you ask yourself, what is the value I had for the critical, for the test statistic? The test statistic value you had was 2.0392. So when you now go back to the section here, you ask yourself that 2.092, will it be in the rejection area here, or to be to the left of this, the white space, which is a non-rejection zone? Well, 2.03 is to the right of 1.645. So it will be in the rejection. So we will reject the null hypothesis. So in the yellow section here, I've indicated that since the test statistic, which is 2.039, exceed the critical value of 1.645, we reject the null hypothesis. Now, at this stage, you have to think, what does the null say? The null says that the average limit, or the average limit is 31, 73. It's not over that. It's capped it at 31.73. We are rejecting that. We are rejecting that. So it means that we are going to make a conclusion that the average limit is actually over the 31. It has gone up beyond that 31.73. So we have enough evidence to support the claim that was made by the researcher. Or if we are the researcher, the claim that we made. So you can now come here and conclude that there is sufficient evidence that the mean credit balance has increased, okay, has increased to 31, or has increased beyond 31.37, using the critical value approach, using the critical value approach. What about using the p-value approach? If you use the p-value approach, you're only going to compare the p-value and then the alpha. As for alpha, we know that to be already 0.05. So all we need to do is to find the p-value. How do you find the p-value? Guys, you've got to pay attention because you use both approaches in your exams. How do you find the p-value? And let me give you a clue. It's easy on how to find the p-value. Always use the test statistic to find the p-value. Write it down somewhere. Always use the test statistic to find the p-value. Let's go to the table again. We are going to use a test statistic. Now remember, our test statistic is 2.039. 2.039. So you are going to look for 2.039. Okay. Any number closer to 2.039 in this space here. Any number. And then you trace it up to find the one tail. Since we are dealing with one tail, the one tail 2. What was the value? I really forgot. 2.03. Now that is one way, by the way. I'm going to show you another way. When you use this approach I'm showing you, it will be tricky, but there's a better way to use. One way to use is turn the 90. What's the name? Yeah. Okay, the 2.039, let's convert it. Let's convert it. Okay. When you convert it, it becomes 2.04. 2.04. Now, you can use the Z here to get that. I'll show you. But it gets smaller. So all of the ones I showed you, they are here. Okay? The hypothesis testing critical values that I showed you, they are here. So just take on this table, you have it. That's the same one you use. So you have 2.04. So let's try to look for 2.04. In fact, let me zoom it in so that you can appreciate it here. We are looking for 0, because 2.039 is 2 decimal. You have to round it to 2 decimal place. So this is 2.04. Watch here. 2.04 is here. Any number closest to it is still 2.04. You keep climbing upward, climbing upward, climbing upward, looking for one tail, one tail, one tail. And guess what you get? You get 0.025. 0.025. That's a p-value. You compare that 0.025 with the alpha. So p-value is 0.025 compared with alpha, which is 0.05. You can see that we have made a smaller error than what we are expected to make. So on the basis of this, we will now say that since the p-value is less than the alpha, we can reject the null hypothesis at a 5% level. Please remember, anytime the critical value concludes, the p-value will conclude the same way. The critical value will lead to the same conclusion as the p-value has done. So there will not be a difference in the two. So that is how you attack this one sample hypothesis question. Okay. Now, there are other ways one can look at it. Take the 100% and then take it out from some other values, and that will also give you the p-value. But there are several ways you can use because we have many tables here. Okay. But the most important thing is that you will get this. And finally, you can conclude that 0.0. The table will not give you the exact thing. I have done this thing already in Excel. Excel will give you the exact value, but the table will not give you the exact value. But don't worry, the 0.025 is the one that you can use for this purpose. Okay, so how do you do this in Excel? It's very simple. You see, the thing about Excel is that one sample is a little bit strange to do. This is my population mean, as you can see here. Just type it there. This is a sample mean, sample size, deviation. This is a standard error. Now, how do you calculate the standard error? In Excel, you use this formula. That is, take this one here. That's the standard deviation divided by the sample size, the square root of the sample size. The sample size is 180, so it's the square root of 180. So you are actually dividing 1,000 by 180. That will give you the 74. The hypothesized mean is that there is no difference. Alpha is that this is a one tail, so you type 1. If not, you type 2. The degrees of freedom is 180. It can change. But let me tell you something. The degrees of freedom here is 180, not 180 minus 1, because this is a large sample. Now, how do you calculate the t statistic? Well, you can see that we take this V2. V2 is 33 minus 25. 3325 minus 31. 3325 minus 3135. All divided by the standard error here, which is actually the standard deviation by the square root of the sample size. But the most important formula for you to calculate is a critical value here. So that's why I'm saying that I use this one to give you the answer, but the table gives you the answer also. But I use this one I calculated in the software to give you the answer. How? You have to type equal to T dot INV, okay, to indicate the value, the test statistic value, critical value that you are calculating. Then you convert the alpha. Alpha is 0.05. You subtract that from 1. Because what you will see that Excel is requiring you to write is rather the confidence interval. So Excel will not ask you to write the alpha. It will rather ask you to find the confidence interval. So it will be 1 minus 100% minus the 5%, okay, which in this case will be 0.95. And then you attach the degrees of freedom. The degrees of freedom is this one. You attach that one there. And once you do that, it will give you the critical value of 1.65. Let me see the critical value that we found. Okay. We got 1.645. Okay. And the one here has given us similar, the same thing actually, 1.65. So that is how you find the critical value. Now, how about the p-value? Well, look at it. You use this formula called T dot distribution dot right tail. We were doing right tail, so you use right tail. Else you see left tail, or you see two tail, whichever one you are doing. That's what you do. And then you select the test statistic, which in this case is 1.65. You select it here. And then finally, you select your degrees of freedom. So you select these two, and that will give you the p-value, which is 0.21, okay, which is what I used to give you in the original one here, 0.21. That's what I decided to give you. But I also used the table to confirm that. So this is how you calculate it in Excel. Good. Now let's go to the last one for today. We are going to look at another scenario that will help you to be able to compute two sample independent situation. Independent. Now, what we just did was just one sample. But now let's look at two samples. Let's say you want to compare the ages of boys and the ages of girls. You believe that there's a significant difference in the two. Your class teacher doesn't believe that. You want to check whether a significant difference exists. You want to check whether evidence that the differences between them are 0 or they are equal. The same thing. If the sample size is greater than 30 or more, then it's large. The sample standard deviation can be big or small. The only difference is that now you have mu 1 and mu 2. If it is lower tail, we know what to do. But watch this hypothesis. This time the hypotheses are in such a way that you either say mu 1 is greater or equal to mu 2, whose opposite will be less than. If it is two tail, look at the hypothesis. Mu 1 is equal to mu 2. Or mu 1 is not equal to mu 2. That is how you formulate. You don't need any number to formulate the hypothesis. It's very simple here. Always keep it in your mind. It's going to be one mu 1, another mu 2 here, another mu 1 here, another mu 2 here. Then you think about it, the symbol. Whether the symbol is less than, is greater than, at most, larger, beyond, above. Those are the ones that you use. Okay. Let's see whether we can try one. Okay. Remember that you have a situation where the standard deviation is known and another situation where the standard deviation is not known. In that case, how you will handle it is this. I'm going to show you where the standard deviation is known. Is known. Okay. If the standard deviation is known, the way you calculate the z statistic is this one. Is this one. Now, this is not difficult. All you need is the mean for the first group, the mean for the second group. Finish. Then you need the standard deviation, the variance for the first group, the variance for the second group. That's it. And then you can put them into this formula and you can find it. If the standard deviation is not known, but the sample size is large, the same thing. It's the same thing. The mean, you find the mean of the first group, the mean of the second group. Then you divide it by the variance of the two, the square root of that. Now, if the standard deviation is not known, but the sample is small, at up here, that one, the formula is quite strange, but it's still the same. You calculate the mean in the first group, the mean in the second group. Then this standard error, you calculate it as this. Again, it's the same thing. You're using the sample in the first group, multiplying the variance, then the sample in the second group, minus 1, multiplying the variance, all divided by this. Then you take the square root of that. This becomes the standard error. Okay, so now, when do you use which of these formulas? Remember, whether it's a one-tail or two-tail, it follows the same principle that we have done. Okay. Maybe, just maybe an example will do. And I have this example in Excel. But I've also brought all of them here. So watch it with me. Follow me as I go through this. That will be done for today. The purchasing manager of a company has noted that they normally order many of the same types of items from two companies. One, from alum sheeting, and two, from durable products. Now, it's believed. So, you see, the moment alum sheeting comes first, you should know that that will be the U1. Durable product will be the U2 because that came second. Okay. It's believed that alum sheeting doesn't have a longer lead time than durable product. In other words, when you order the product, okay, alum sheeting, a short time it will get home. That's a belief. And then the durable, it takes a rather longer time for the items to come. That's a lead time. Yet, if the lead time is significantly longer, that is the lead time for alum sheeting. If it is longer than the durable, managers will drop alum sheeting. Note that the time between the placement of the order and the arrival is what is known as the lead time. We are going to test the hypothesis of supply lead time performance. Like which one, that when you order, they'll bring the things quickly. Is it alum sheeting or is durable? Should the purchasing manager drop alum sheeting? Well, we know that they can only drop it if the lead time is too long. Formulate the hypothesis. Use all the critical values and let me know. Now, how do you do the formulation? Well, first thing, you got to realize and understand what you are talking about. The most important thing in hypothesis testing is knowing whether you are dealing with the symbol you are using. If you get the symbol, you get everything. If you don't get the symbol, you get nothing. So let's try to understand this. Based on the little you have already seen, is this looking like a two-tail or a one-tail for you? Who can tell us? Just on top of your head, looking at the words, is this looking like a two-tail or a one-tail for just on top of your head, though? Don't think too much. Two-tail or one-tail? Yeah, can be two-tail or one-tail. Very good. It's one-tail. What is the key word that made you say what you said? Which word? Which word was that? Longer. Very good. No, Henrietta, there was no one tail mentioned in the sentence here. So you can't say one tail guided you. I'm saying which word was guiding your thought. And that is the word longer. Good. So if it is longer, then you will have new one longer than new two, and then new one not longer than new two. This is how it's going to be. And in this case, the null hypothesis will be the one below because it carries the level of equality. And the alternative hypothesis will be above. So what does the null say? From what you are seeing, the null is saying that the lead time for alum sheeting is lower, or let me put it, the lead time is at most that of the lead time for durable. Remember, alum sheeting is the first one. So the lead time for alum sheeting is lower, or better still, is at most that of the lead time for durable. Whereas the alternative is saying that the lead time for alum sheeting is longer than that of durable. So that's what the null is saying. Now, the next thing is identify the data set. Let's go and see the data set. Okay, so look at the data set here. So here, let's look at the data set, then we can understand which test to use here. So now you can see that you have the alum sheeting. This is a lead time. The first time that it was ordered, it took 6 hours to deliver. But the next one, it took 6 hours to deliver. 9 hours, then 7 hours, then 7 hours, then 5 hours, then blah, 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 blah. Durable, we did a lot of ordering from them. 3 hours, blah, 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 blah. It's looking like durable is looking good, eh? But we shall test it. How do you do it? Well, we need to first of all calculate the mean in each group. That's the first thing, okay? So the null hypothesis is that maintain alum sheeting because it has a lower lead time. Remember what I wrote, I've switched them. I brought the null first. It has a lower lead time. Or better still, the word should have been, it has at most the lead time. Drop it, since durable is rather better in lead time. Now, when you come and write it, you write it like this. In fact, when you take this one to the right-hand side, when you take this to the right-hand side, you see that alum sheeting has equal or lower lead time than durable. And then the opposite will be this, okay? It means that that company is not doing well when it comes to early delivery. This is a one-tail testing, once again. Okay. You have to calculate the sample. You have to count the sample. If you look at it carefully, this is 1. You can count them with your eyes. 1, 2, 3, 4, 5, 6, 7, 8. That's the sample size. And here the sample size is 13. So you have your N1 and you have your N2 ready. Next one is to find the mean. The mean is add everything here and divide it by the 8. And then add everything here and divide it by the 13. If this was an exam condition, you have to do these things yourself. Okay, so this is it. When you do that, you find the mean for the first one to be 7, the mean for the second one to be 4.9. But we have to test to see whether, because the fact that this one is 7 alone means that it looks like alum sheeting is going to be dropped. It's going to be dropped because the lead time is taking too long. But hey, you have to juxtapose that against the standard deviation. So let's see. The standard deviation here is 2 for the alum sheeting and also 0.757 or 58 for the durable. So you have all your parameters. Okay? So you calculate the T statistic. What I did was to substitute it into the formula. Now, which formula will you take? Look at the sample. 8, 13. If you go to the formula table and you have to select formula, you check it. This is the first formula. Okay, this is the second formula. Okay, and this is the third formula. Which one do you think we'll use? First, second, or third? First formula, second formula, third formula. Frederick says second. Okay. Let me go back. That I'll show you. Okay. So this is that. This is the first formula here. And the first formula is sigma 1 and sigma 2 are known. Second formula is where they are not known, but they are greater than 30. Third one, they are not known, but less than 30. Which formula are you going to use? Which formula? First formula, second formula, third formula. Which one? Well, it's a third formula, just to give you an idea. It's less than 30. Look at it. The N1 or N2 are less than 30. Our own one is what? One is 8. One is 30. So this is it. This is the formula that you use. This will be 1 over 8 plus 1 over 13. This one will be 8 minus 1. Okay. And then this one will be that. Now, how do you get these formula? S1 is very, very simple. Okay. And you'll see how to calculate that pretty soon. I'll show you. Okay. Oops. So these are the values that you get. You should know how to easily calculate standard deviation. Okay. Yes, Samuel.
Oh, please, I wanted to confirm there's 0.5769 there. Shouldn't it have been S2 squared instead? Or that's how it's supposed to be?
Shouldn't it have been
S2, because I see S1 equals 2.
Oh, sorry, you're right. It's a typo. It's this one. It's supposed to be S2. That's what you mean. Yeah, Frederick.
So I wanted to ask why we are not using the first formula since we can derive the standard deviation. So we have the standard deviation here.
Say that again. The standard deviation is unknown. For the first formula, the standard deviation is not even known at all. Here we know it. We can calculate it.
Yeah, the first formula said when the standard deviation is known, but the third one said it's not known.
Yes, but most of the time we don't know. This data, oh, mind you, the word known here means that you don't even have data. Oh. You get it? Yeah, you don't have the data for it.
Oh, okay. So it's given in the question when you don't have the data.
Exactly.
Oh, okay. Thank you for the clarification.
All right. So when you work it out, you are going to get this. When you substitute all of them into the formula, you're going to get T equals to 3.8280. That's, I mean, this test statistic that you see, that looks manya here. Okay. This one, that is the one we have just broken it down to the 3 point. Where's that? That's the one we've broken it down into this value, 3.8. Once you get this one, now you need to find this. Okay? You need to find this value. This value is a critical value. And the critical value is found by, first you must know your alpha. Okay. What is the value of the alpha? Please note that this critical value we are finding, when you match it together with the alpha, it gives you the degrees of freedom. So the whole of alpha n plus n1 plus n2 minus 2. All of it is called degrees of freedom. So this one. So this one is going to be alpha, which is in this example. Was alpha given? Please note that whenever alpha is not given, alpha is 5%. So you can see that here, alpha was not given. So when alpha is not given, the default alpha is always 5%. Okay, so let's take this one. You're going to get 0.05. And then you take 8 plus 13 minus 2. That becomes 8 plus 11, I think is 19. Okay. Okay, so it looks like alpha was given as 0.01. So what is that? Oh, yeah. Oh, wait, where is it? Okay. Well, it appears that it was given, I gave it, but I did not document it here. So in this case, alpha is 1%. Take note, alpha is 1%. But if it is 1%, it will be written down for you. So don't worry. Alpha is 1%. So how do you get a 1%? And look at the value. We are getting 1% or 0.01, matching it against 19, I think. Okay, 18. Okay. So you're matching it against 18, you get 2.18. Now, how do you get that? Let's go to the table. Because you want to learn how to get these values, because when you're on your own, it might be a little bit daunting. On the far left here, you will see 18. Okay, look at it, 18. And then you are looking for 0.01 against 18. Where is that? 0.01 against 18. What do you get? Can somebody type it there for me? (0.01) against 18. Let me see this one too. Did you get it? I think somebody has typed the right answer. Okay, good. So now let's go here. Why did I get this? It's supposed to be 0.01 against 18. Yes, Della.
Doc, please. We said N1 was 8, but in the formula you are using 7. Is that a typo?
Yeah, I think that might explain why. Please, just a second. Let me just correct this. So it's supposed to be 8. 8 plus 13 is what?
21.
21 minus 2, 19, right?
19. So the 7 was the mean, right?
Okay. Let me see the table. So again, 19. And then 0.01. Okay. Yeah, I think that was a typo. In fact, even the one, I decided to confuse you guys, not knowing that the original one was. So I'm going to put it there, use 1%. Use alpha equal to 1%. So that, oops. Okay. So let me share the screen. So I have used alpha equals to 1%. And now let me show you. So you have T018 plus that. So that will give you 19 instead of 18. So now let's go to the table. So this is a table. Oh, you guys can see. And now we are going to select degrees of freedom, which is 19. So look at degrees of freedom, 19, 1%, one tail. What do you get today? What value do you see? Okay, good. So I see most of you are indicated 2.539. Okay, 2.539. So let's go here. You have that value to be 2.539. Now, when you look at a critical value, which is 2.539, compare it with a t-statistic, which is 3.8, which one is bigger? Is a test statistic. Whenever the test statistic is bigger than the critical value, you reject the null hypothesis. Okay? You reject the null hypothesis. So, in fact, it was obvious. We are going to reject alum sheeting because it's taking too long a time, okay, to indicate this, to indicate that is reliable in this case. Okay. So we have a conclusion. I'll come to the p-value, but we have a conclusion. Reject the null hypothesis and conclude that alum sheeting has statistically longer average lead time than durable product. Now, let's quickly go to how to find the p-value. We always say that use a test statistic to find the p-value. So take this 3.82. So let's go to the table and look for 3.82. 3.82 is on the far right here. 3.82. That should be somewhere here. Okay, 82 is somewhere here, as you can see. That is 3.819. Okay, but all the numbers above it or below it, you look at it from here, then you trace it up. And when you trace it up, you're going to get this value. Look at it. You're going to get 0.305. When you round it to the next number, it will be 0.001. 0.001. Okay, so that is a p-value. So you can see that the p-value will be approximately 0.001. And then alpha was 0.01, 1%. So should we reject it now or we don't reject it now? Based on this, you can see that our mistake is too small. We have made a very little mistake. So we have enough confidence to reject the null hypothesis. We even made less than 1% mistake. So we will reject the null hypothesis, which says that we should maintain alum sheeting. Now we can conclude that we don't need to maintain alum sheeting, just like the first one did. And you can see that all of the values we have are here. If you go and do this in Excel, choose this one. When you go to data analysis, you select two sample, assuming on equal variance. That's the one you use. Okay. And then you can enter the range for the first data, enter the range for the second data, which I did here. Then you will get this result. Watch it. You get this. You just check. It will give you the sample observation for the first one to be 8, for the second one to be that. And then it gave you the, obviously there will be differences because the table is different from that. We are not interested in the two tail, we are interested in the one tail. So look at the one tail result. That's closer to the one we had for the p-value, 0.001. We had 1, and this one will be 2. Okay. The test statistic, we all had the same thing, 3.827 or something. Okay. And then the critical value. The critical value here is 2.76. What did we have? Okay. The critical value was 2.539. blah, blah, blah. Again, the table will give slightly different results from the software because the software is very precise. So that is how you do this in Excel. There are several other ones you can do in Excel. For example, you can do two sample tests. That is Excel procedure. You can also do paired. But most of these ones, I will not do it here. Second semester, you will learn about the paired. Everything we've done here is on paired or independent. When you get to second semester, you'll be doing the paired or the dependent. But this was just to give you an idea. Watch this. This is just to give you an idea. They can do one sample hypothesis. You can do two different sample hypothesis. In fact, you can do 3 different samples, which is called ANOVA. We didn't do it. We will not do it this semester. We'll do it next semester. Okay. Where you now compare 3 or more samples together. We do that. So all of the, and then there are non-parametric versions are also in the next semester. But this is just to give you an idea of how to hypothesize. So take note of these 2 hypotheses, 1 sample and then 2 samples. All of them independent samples. Not dependent, but independent samples in both cases. Finally, these are the hypothesis testing steps. The steps are clean. Go through it in a beautiful chart. If you are doing practical work, formulate the hypothesis, select your test, select alpha, collect the data, calculate the test, find p-value, compare with alpha, or find critical value, compare with the test, reject or don't reject. These are the steps. Okay. And now this is a flow chart of whatever test you ever want to do, ever, in normally distributed data. It tells you if your data is univariate, then use this one, then do this one, then do this one, this one. If it is bivariate, then go here, go here, go here, go here, go here. The last 2 at the bottom here is what we shall do next time. Ladies and gentlemen, that brings us to the end of the entire cover. I have a kind of a homework for you to try your hands on. Okay. This is a beautiful data set that I've given to you about public universities and private universities. Provide a descriptive statistics of each data, formulate and present the rationale for hypothesis, compare the difference in annual cost between public and private, undertake statistical hypothesis testing using both the critical value and p-value approach. Do a similar exercise in Excel. What is your recommendation for GTech? Because this was about GTech. Don't submit it. Try your hands on it. It's for you and for you alone. Ladies and gentlemen, that brings us to the end of the entire Abudo. Now, next Saturday, we are meeting. Okay?